In this part of the unit on the introduction to electronics, we're now going to consider conductors, semiconductors, and insulators. So we're going to begin by looking at the first one, which is to distinguish between conductors, semiconductors, and insulators. Now, all materials, all electronic materials in particular, consist of these three: conductors, insulators, and semiconductors. So let's have a look at each one and see what the specific nature of these individual materials are and how they compare with each other. So let's begin by looking at conductors. Well, conductors tend to have low resistance, and we saw when we looked at the unit on current electricity that this essentially meant that in a conductor, the flow of electrons through that conductor was not impeded to a great degree. In other words, there was a relatively easy flow of electrons through the conductor. There wasn't any real resistance, or if there was, it was relatively low compared to, say, an insulator. So in other words, conductors have low resistance, which allow electrical current to flow. And an example of where this is the case is in elements or materials such as copper, silver, gold, aluminium, and nickel. So these are examples of conductors which have low resistance. Now if we cross over to insulators, insulating material tend to have high resistance. In other words, they impede or they suppress the electrical flow of current. And so when we talk about an insulator with high resistance, we can quote, for example, glass, ceramics, plastic, and even wood. So these are examples of insulators. In terms of semiconductors, well, semiconductors can allow or suppress electrical current flow. In other words, they behave in the same way as conductors and insulators to some degree. So in a way, they're kind of a cross between the two. They can allow or they can suppress electrical current flow. And an example of a semiconductor or materials that are used in semiconductors are carbon, silicon, and germanium. Now, how does this compare to semiconductors? Well, semiconductors also contain a pool of delocalized electrons. So you have a flow of electrons within a semiconductor. And this flow of electrons, or delocalized electrons, allow current to flow. However, with semiconductors compared to metals, for example, or conductors, semiconductors can also contain a group of atoms with an unusual low number of electrons. And these regions within the semiconductor, or in terms of these regions of atoms, they contain what's called holes. Now I'll explain to you what holes are in terms of the significance of them in semiconductors, but essentially holes are positively charged, and they are able to flow through a semiconductor just in the same way that in a conductor or in a metal you have a flow of delocalized electrons. So in a semiconductor, you still have a pool of delocalized electrons, but in addition to that pool of negative delocalized electrons, you also have localized positive holes. And these positive holes are able to move or flow through the semiconductor. So their formation leaves an opposing fixed charge behind them. So in other words, when you see holes, normally what happens is these holes will have a positive charge. Now, semiconducting material, they're usually artificially modified to adjust their conducting ability. And this is usually done by adding extra holes or electrons to their structure. So conductors really are just materials which are able to conduct electricity because of the free movement of electrons. Now it's important to note that these electrons originate from the valence shell of the atom, which is the outer shell of the atom. In fact, the electrons which are in the inner shell of the atoms in a conductor, they're held extremely tightly by those inner shells. So when we talk about the ability of a conductor to conduct electricity to allow electrons to flow, we're really talking about electrons which have their origin in the valence shell, the outer shell. And so this is a classical example in terms of the internal structure of metals. They have electrons in their outer shell which are held less tightly than the electrons in the inner shell, and subsequently those electrons are easy to be removed from that outer shell and form a sea of delocalized electrons. Now when we come to semiconductors, as we mentioned earlier, semiconductors do indeed have a number of electrons from their outermost valence shell which have enough energy to actually break off. And in fact, these electrons are able to break off and they enter what's known as the conduction band. Now, the conduction band really is electrons which have a specific amount of energy and they're able to move off an atom in order for them to conduct. So in other words, semiconductors do have electrons which are able to break free from their parent atom, but this tends to happen when there is an increase in thermal energy. In other words, when the material becomes hotter. And examples of this type of material are silicon, germanium, lead sulfur, selenium, and gallium arsenide. So these are examples of semiconductor type materials which tend to have this ability. And those which have things added to them in terms of elements and other materials, and these are called extrinsic semiconductors. And we're going to have a look at the difference between the two. So substances such as silicon and germanium, they are considered to be pure semiconductors. Now, if we look at the structure, the atomic structure of silicon and germanium, you'll see that from the periodic table that they have 4 valence electrons. And these valence electrons are used to form what's known as covalent bonds. So at low temperatures, these particular semiconductors, germanium and silicon, they act as insulators. They do not allow the flow of electrons through them. However, when silicon and germanium are heated, when thermal energy is applied to them, then the electrons which are in the valence shell, they detach and they break free from the covalent bonds that are formed between the atoms. And as a result of that, positive charge is created as the electrons leave the atom. Subsequently, holes are formed, and holes are the lack of an electron at a position where one would normally exist in an atomic lattice. So the heating up of a silicon or germanium structure results in electrons leaving the covalent bond, and as a result of that, holes are formed within the structure. Now we can visualize this as follows. When an electric field is applied to a semiconductor, in other words, when it's connected up to a battery or a power source, then the electrons in the holes, they tend to move in opposite directions. And as a result of this, the semiconductor demonstrates what's known as intrinsic condition. So by connecting up your semiconductor to a battery source or a power source and applying a potential difference, across the silicon or the germanium in this case, then you'll get movement of the electron and movement of the hole in the opposite direction. And you can see in the diagram, this covalent bond, because of thermal energy being applied to the silicon or the germanium, has resulted in the electron, which is used to form that covalent bond in terms of sharing of electrons. One of the electrons actually moves away from that bond. And as a result, a hole is formed where there was a covalent bond. When we talk about a silicon crystal, we need to look at that in comparison to, say, an insulator. Why is a silicon crystal different from an insulator? Well, the reason is that at a temperature above absolute zero, there is a probability, a small one, but still a probability, and it depends on the temperature, that an electron in the lattice will be knocked loose from its position, and that will leave behind an electron deficient hole. In an insulator, that could happen at high temperatures, but in a silicon crystal, that happens to some degree when there is an increase in temperature. Not necessarily the case always with an insulator. So here you can see in the diagram we have silicon atoms forming covalent bond with each other to form this lattice structure. And here you can see the black circles represent the electrons forming the covalent bond. And these become free electrons when thermal energy is applied, causing those electrons to leave the covalent bond and leave behind these holes represented by this circle. So we've looked at pure semiconductors in the form of silicon and germanium, which are called intrinsic semiconductors. Now let's have a look at impure semiconductors. Now, how do we make a semiconductor, a pure semiconductor like silicon? How does that become an impure semiconductor? Well, the answer is by a technique called doping. And doping is the deliberate introduction of an impurity into a semiconductor which changes its electrical property. Now, there are two types of impure semiconductors, depending on the nature of the impurity that's introduced into the intrinsic semiconductor. And these two types are called N-type and P-type. So let's have a look at a N-type semiconductor. Now, if you have what's called a pentavalent atom, then that means you have an atom that has 5 valence electrons in its outermost shell. And examples of pentavalent atoms are phosphorus, which has 5 electrons in its valence shell. So if you take a pentavalent atom like phosphorus and you introduce it into a pure semiconductor like silicon, then the phosphorus will make 4 covalent bonds, just like the other silicon atoms. But the only difference is that phosphorus has 5 electrons in its valence shell, which means it will have an extra electron, it will have an extra negative charge when it's introduced into the silicon. So the silicon will have, in addition to the silicon atoms, it will have a number of phosphorus atoms which will introduce an extra electron in the lattice. And because it's introduced as an extra electron, we call this a negative type semiconductor, N representing negative. So this electron here, this electron which is introduced by the phosphorus, this becomes a free electron, and it's available to conduct electricity. As a result of that, the doped silicon, as we call it, that becomes a N-type semiconductor, and the N stands for negative. Now let's have a look at another type of semiconductor, which is called a p-type semiconductor. The difference between this type of semiconductor compared to, say, the n-type semiconductor is that the major carriers are what we call holes. So let's explain that in terms of how we came to that assumption. Let's say, for the sake of argument, that we introduce boron atom into the silicon lattice. So what will happen is that the boron atom, which is this atom here, will replace one of the silicon atoms. And if you look at the periodic table, what you'll find is that boron actually has 3 electrons in its valence shell. Now remember, silicon has 4 electrons in its valence shell. So the fact that you've now introduced an element which has 3 electrons in its valence shell means that there's going to be a missing electron in the lattice of this semiconductor. What will happen is that missing electron will create a hole. And what we say is that boron, or the boron atom, is an acceptor. It's an acceptor because what will happen, it will accept electrons from the other silicons because it's deficient of an electron. It's only got 3 electrons in its valence shell. So what will happen is that electrons will move to fill this hole. But in so doing, the silicon atom will leave behind a hole because the electron, for example, that's here will move to fill this hole. So we then create another hole here. So this is called a p-type semiconductor because we now have positive holes which have been created as a result of electrons moving to fill the vacant hole which is here in the boron atom. In this part of the unit on Introduction to Electronics, we're going to focus on semiconductors. In particular, we're going to focus on impurities and doping. Now, when we talk about doping, what we really mean in an electronic sense is the addition of materials to an intrinsic semiconductor or a pure semiconductor, which has the property of enhancing the characteristics and behavior of that semiconductor. So let's begin by looking at p-n junction diodes. Now, in order to understand a p-n junction diode, you need to understand p-type semiconductors and n-type semiconductors. And in the previous section, we looked at these in detail, explaining how p-type semiconductors are formed and how n-type semiconductors are formed. And you should remember that p-type semiconductors are semiconductors which have positive holes as their major carrier. And n-type semiconductors are semiconductors which have electrons as their major carrier. So, when you bring these two together, what you obtain is a junction. So, when these two semiconductors, the p-type and the n-type, are joined together at this region, then you have what's called a junction being formed. Now, around that junction, some very interesting things happen. And what we obtain at that junction is something called a depletion region. And so we're going to have a look at the mechanism by which that depletion region is formed. What exactly is a depletion region? What is the benefit of a depletion region in a p-n junction diode? What is a diode? So all of these questions are going to be answered as we go through this particular section of the unit. Now, the simplest semiconductor device is in fact called a diode. And a diode consists of a sandwich of p-type and n-type semiconductors. If you look at the diagram here, you can see that we have exactly that. We have a p-type semiconductor on the left-hand side, and we have an n-type semiconductor on the right-hand side. So what we effectively have is a sandwich of p-type and n-type semiconductors. Now, in reality, rather than having two separate pieces of doped silicon and then joining them together, the reality is that in the manufacture of these diodes, a single sample of the intrinsic silicon is treated first with the N dopant, which is essentially just the N impurity that you add. For example, if this was the N dopant, this would be probably phosphorus added to the silicon. And then it's treated again with the P dopant. So this would be probably, for example, boron. So once that is done, metal contacts are then attached to the ends of this doped silicon. And then wires are attached to it. And then they're connected to positive terminals or negative terminals. Now, what's important really in this particular setup is that the boundary between the P-type silicon and the N-type silicon, this region is called the junction. So that line here is actually the junction between the P-type and the N-type silicon. Therefore, what we have in effect is a p-n junction diode. Now, if you look very carefully at the diagram, you should be able to see that the free electrons, which is this one here, caused by the addition of the N dopant, let's say, for example, phosphorus, because phosphorus has 5 electrons in its valence shell, then it's going to produce one extra electron which can roam around this silicon region, which has the phosphorus in it. In the same way that this region here, which has boron, which is an element which only has 3 electrons in its valence shell, therefore you're going to have a deficiency of electrons, so you're going to have in effect a hole created, a positive hole. So effectively, the free electrons on the N side of the junction, they're going to be attracted to the positive holes on the P side. Now what will happen is that the holes from the P side will move towards the N side, and the electrons from the N side, they're going to move towards the P side. Now when this happens, the electrons on the N side that are moving over to the P side, they will recombine with the holes. And similarly, the holes which are moving over to the N side, they're going to recombine with the electrons. So what will happen is that you end up having on the P side, due to the migration of electrons, you're going to end up having electrons near that junction, a buildup of electrons. And similarly, on the N side, you're going to have a buildup of positive holes. Now, as a result of this buildup, what you find is that these charges, for example, the negative charge at that junction, they're going to produce a force in the opposite direction, which means that any more electrons that try to migrate over to the P side, they're going to experience a repulsive force with the electrons in this depletion area. And similarly, any of the positive holes that try to move over to the N side, they're going to experience a repulsive force due to the buildup of positive holes in that depletion area. So because now there's no charge in this area, because the charges are cancelled out in the depletion area, because they have no charges, there's no charge carrier, then it's going to be a very poor conductor of electricity. Thus, when we talk about a junction diode, we can say that it consists of relatively good conductors at either end, in other words, this area and this area, but the middle consists really of a poor conductor. Now, in this animation that we're going to have a look at, you can see what we've just talked about happening. You can see the migration of electrons from the N region to the P region, and you can see also the migration of the holes from the P region to the N region. So here you can see the migration of the electrons from the N side to the P side. So we now have a buildup of electrons on the P-type side near the junction. So you can see that happening again here. And so you can also see there's a buildup of positive holes on the N side. So semiconductors, which are essentially N-type and P-type, are brought together, as in this animation. And then if you watch carefully, you'll see that when they come together now, that we have a situation whereby electrons and holes migrate across the junction, as in the animation, and a depletion layer is formed here. Then a potential difference is set up across that junction, because you now have one side of the junction being negative, which is this side here on the P-type, and one side being positive in terms of the charge buildup. So that causes a potential difference across that depletion area. So at the junction, the N-type electrons, they move into the P-type holes and vice versa. And this forms what's called a diffusion current. Now the middle of the PN junction, that acts as an insulator. And as we said before, that forms a layer, which is called a depletion layer. And we've also mentioned that the potential difference formed across the depletion layer, that is now called the barrier potential, since it prevents any movement of charge carriers across that depletion layer.